Hey everyone, Ricardo here. So in this video, I'm going to be showing you how a permissive overreaching transfer tripping scheme works, which is commonly known as a POTT scheme. Now these are protection schemes where the two ends of a transmission line communicate with each other to create a high-speed tripping scheme that will only trip for faults inside of the transmission line. So in this video, I'm going to be going over how POTT schemes work, and then towards the end of the video, we're going to see how we can implement this type of scheme using the SEL-411L relay. Now just real quick before we get started, make sure to download our Protection and Control Fundamentals PDF. It's a 28-page PDF where we go over all the fundamentals about protection and control, so make sure to check it out. The link is in the description below. So as I mentioned, a POTT scheme is a communications-assisted tripping scheme where the two ends of a transmission line communicate with each other to see if there's a fault inside of the transmission line. Now in this type of scheme, each end of the transmission line implements an overreaching element. That is an element that reaches beyond the end of the transmission line to see whether there's a fault in the forward direction from its perspective. So in this way, both relays at each end of the transmission line can detect a forward fault, and then they can share this information with each other to determine if the fault is inside of the transmission line. Because of course, if the fault is forward from both directions, then it must be inside of the transmission line. So I know that might be a little bit confusing, so let's go over an example to see how this works in a little bit more detail. All right, so let's say, for example, that we have a transmission line that looks like this. So we have a local bus here. We have our breaker over here for the local substation. We have our transmission line, then a breaker at the remote end, and this over here is going to be the remote bus. And again, in this case, we're going to be using two SEL-411L relays for our example, one at each end. So let's say, for example, that we have an SEL-411L relay over here and an SEL-411L relay over here. So each one of them, of course, is going to be reading currents from the local end. So we have our CTs over here, and of course, we also need voltage. So we also have our PTs. In this case, they're going to be on the line side of the breaker. Now, in this case, let's say that we have our transmission line is 10 ohms at 85 degrees. And here for simplicity, I'm going to be using secondary ohms for our transmission line. So the impedance of the transmission line is 10 ohms at 85 degrees. And in this case, a typical distance protection scheme would be to set the zone 1 element that underreaches the remote bus. Let's say, for example, that here at the local end, we set our zone 1, and let me actually use a different color. So our zone 1 would look something like this, where we set it basically 80% of the transmission line length. So it underreaches the remote bus. And this typically would have no delay. We would trip instantaneously if that zone picks up. And then we would also have an overreaching zone, which is the one that we're going to be using for the POTT scheme. And so let's say, for example, that we set that to 120% of the transmission line. So some number greater than the length of the transmission line. Again, this is an overreaching element. Overreaching meaning that we're reaching past the remote bus. So we're going to see faults that are beyond the substation at the remote end. Now, typically this would have a delay of, let's say, 30 cycles. So again, in this case, our zone 1 would be 80%, so 8 ohms at 0 cycles, so instantaneous. And our zone 2 would be, let's say, 12 ohms, so 120% of the transmission line at, let's say, a delay of 30 cycles, so half a second. And in this case, although the zone 2 has its own delay whereby it would trip again without supervision at 30 cycles, we can also use this element as part of the POTT scheme. And in this case, the local end would send a signal to the remote end when its zone 2 picks up without the delay. So anytime the impedance of the fault falls within the zone 2 circle, the local end is going to send this information to the remote end saying, hey, I'm seeing a fault in the forward direction. Now, how this information is sent to the remote end varies per application. It could be done via, let's say, direct fiber communication or through line traps or any other communications device. But the important thing here is that, again, both ends are going to send this information to the remote end when their zone 2 picks up in this example. Now, note here that because the zone 2 overreaches the remote end, it doesn't know if the fault is in fact inside of the transmission line. So we could potentially be seeing a fault, let's say here at the remote bus. The local end doesn't know that. It only knows that it's seeing a fault in the forward direction, somewhere in the vicinity of the transmission line. But it could potentially be beyond the transmission line. So this is what we call this an overreaching element. Now, if we do the same thing at the remote end, and let's actually go ahead and draw it over here. Again, a typical scheme here would be that the zone 1 of the remote end would be set to 80% of the transmission line, and the zone 2 would be, let's say, 120% of the transmission line. So we can do the same thing at the remote end. And what we can do then is that anytime one of the relays both sees its zone 2 pick up, so it's seeing a fault in the forward direction, and it gets a signal from the remote end saying that its zone 2 also picked up, then we can trip instantaneously without no delay, because that would mean that the fault is inside of the transmission line. So again, the key point here is that both ends are seeing a forward fault. So the local end is seeing a fault in this direction, the remote end is seeing a fault in this direction. So therefore, it must be somewhere between those two devices. So it must be somewhere here in the middle. So let me actually use a different color. So again, if both ends see faults in the forward direction, the fault must then be inside of the transmission line. So let me actually get rid of some of these lines over here. So in this case, then when both ends see a forward fault, we can declare a trip without any further delay. All of this would ideally happen within 2 or 3 cycles, so within a few milliseconds, let's say 50 milliseconds, which is much faster than the delay of the zone 2 without supervision. So if the zone 2 at the local end, for example, picks up, it would start timing, and if it still sees the fault after 30 cycles, it would go ahead and trip even though it hasn't received a signal from the remote end. But if it receives a signal from the remote end, it would go ahead and trip as soon as it gets the signal. And all of this should ideally happen within 2 or 3 cycles. And then of course we would add another 3 cycles for the break clearing time. But the trip decision could be made as fast as 3 cycles as opposed to 30 cycles for the time delayed zone 2 element. So this is why a POTT scheme is much better. It provides much faster protection than just simply tripping without communications with the remote end. Now, what I also did here is I created a spreadsheet. So let me actually go ahead and show you that, which is this one that I have over here, where you can plot the line impedance and the local and the remote end zone 2 elements to see what the overlap is. Now, the area where both zone 2s, again, the local and the remote ends overlap, is where the high-speed tripping would happen from the POTT scheme. So again, in our example, we have a transmission line, which is this line over here, that is 10 ohms long at 85 degrees. I've programmed that over here. And then we're setting both our zone 2s at the local and at the remote end to be 120% of that impedance. So 12 ohms, which I have over here and over here. And just for completeness here, I included also the delays, but of course that's not going to play into the POTT scheme. Now the local zone 2 would be this element over here, and the remote zone 2 would be this one over here. And you can see that the remote zone 2 starts over here and the local starts over here. So of course, one is seen from one side to the other. In our drawing that we drew previously from left to right, the remote end is seen from right to left. So from the perspective of the local zone 2, in this diagram, forward would be in this direction. And from the perspective of the remote zone 2, in this diagram, forward would be in this direction. So just something to keep in mind over here in this diagram. So basically, again, here, the zone where our high-speed tripping would happen is where these two zones overlap. So basically, this area over here, where again, you can see that the two circles overlap with each other. Now note here that it is also important to include some overlap so that we can detect any fault in the transmission line, including any potential fault resistance or fault impedance. Now I'll make this spreadsheet available for download in case you want to use it for your own applications. You can download it using the link in the description below. Alright, so that's the theory about how POTT schemes work. Now let's see how we can program this using the SEL-411L relay. Alright, so what I have over here are default settings for an SEL-411L relay. And in this example, we're going to be programming the local end, but of course, programming the remote end is going to be a similar process. And in here, I just want to mention that we're going to be focusing on the POTT scheme specifically. Although we would, of course, need to program other settings if we were to use this for a real life application. So we would have to program things like overcurrent settings, for example, ground overcurrent, phase overcurrent, add those to the tripping equations, program the front panel, program port settings. There's a lot more settings here than just the POTT settings. For this example, I'm going to be focusing only on the POTT settings. Now, going back to our diagram over here, we need a little bit more information. For this example, we're going to assume that our CT ratios, the current transformer ratios, are 2000 to 5. And this is going to be the same for both ends. So these two are 2000 to 5. And let's say that this is a 230 kV transmission line. So our PTs are going to have a ratio of 2000 to 1, which is typical for a 230 kV line. So again, just remember these numbers. The CT ratios are going to be 2000 to 5, so 400 to 1, and the PT ratios are going to be 2000 to 1. So now let's go back to the settings file. And in here, there's a bunch of settings that we need to program. Again, we're going to be focusing on the POTT settings, but we need to program some things to be able to implement a POTT scheme. First thing that we need to do, of course, is to program the CT ratio and the PT ratio. And you can find that here under Group, Set 1, Line Configuration. And just for the sake of this example, we're going to assume that both CT inputs and both PT inputs have the same ratios. So our CT ratio again is 2000 to 5, which is 400 to 1. So we need to program this to 400. This is going to be 400 as well. And the PT ratios are 2000 to 1, which are actually the default settings here on the SEL-411L relay. So we can leave those settings. Now, the other important thing here is the magnitude of the transmission line and the angle as well. So we said that our transmission line is a 10 ohm transmission line at 85 degrees. Now for this example, we're going to be focusing on the phase distance elements, not necessarily on the ground distance elements. Typically you would set though ground distance protection as well, but we're going to be focusing on phase protection for this example. So let's say for example that our zero sequence impedance is, let's say 30 ohms at 70 degrees. This is typical for overhead transmission lines. The magnitude of the zero sequence impedance is usually somewhere around 3 times the magnitude of the positive sequence impedance. So I'm just putting here typical settings. Again, we're not going to be focusing on ground distance for this example. The key settings here are the 10 ohms at 85 degrees for the positive sequence impedance of the transmission line. All right, so now we can jump into the POTT settings. That's going to be here under relay configuration. And then if you go down to trip schemes, you'll see over here the POTT scheme. Now you'll notice here that all of these settings are grayed out, and that's because we haven't enabled the POTT scheme. To do that, first you need to go to relay configuration over here and then go down to the ECOM, so enable communication schemes. So I'm going to go down over here to where it says ECOM over here, enable communication settings. And we're going to program this again to a POTT scheme. Here you have some other options, DCB, which is directional comparison blocking. You have DCUB, and then there's options as well for the types of channel communications. For this example, we're going to be using a single channel POTT scheme, which is this setting over here, POTT. All right, so now we can go down to the trip schemes, and you'll notice over here that now the POTT settings have been unlocked. So now we can program this. Now here you can scroll down to PT1. So here is the general permissive trip received from the remote end. This is an important setting. So basically what this is this is the signal that the relay is going to see whenever the remote end sees a forward condition. In other words, when the remote end sees a forward fault and its zone 2 picks up, it's going to send a signal to the local end, which we need to program here in the relay. So basically this could be an input on the relay. This could be communications via fiber, but whatever word bit is telling us that the remote end has picked up, we need to program this here so that the relay knows when the permissive signal has come in. For our example, we're going to be using direct fiber communications. So I'm going to program this to RMB 1A, which is mirror bits 1A. Mirror bits is an SEL proprietary channel that works over serial communication. In this case, we're going to be doing fiber over the 2 ends of the transmission line. So whenever each end of the transmission line detects a forward fault, it's going to send a signal via fiber via this mirror bits channel, and then when the local end receives that, this relay word bit, so basically this logical tag, is going to pick up and it's going to become a logical 1. So whenever this relay sees the bit RMB1A being a logical 1, that means that the remote end has seen a forward fault with its zone 2 element. Now here I skipped over the MO elements. We of course need to program that. So let's go over here to MO phase distance element reach. This is where we program the reach of the MO phase distance elements. For this example, we said that we're going to set our zone 1 to 8 ohms, our zone 2 to 12 ohms, and then our zone 3, in this case, since we're implementing a POTT scheme, that's going to be important if we're implementing the current reversal part of the POTT logic. I'm going to leave that out for this example because that gets a little bit more advanced. But typically this would be some number much higher than the remote end. So if we program the remote end at 12 ohms, this could be something like, let's say, 30 ohms in the reverse direction. Again, I'm going to leave that part out for this example because that gets a little bit more advanced. What I want to focus over here is this setting over here, the reach of our zone 2 element in the forward direction, which again, we said we're going to program that to 12 ohms for this example. All right, so we programmed our reaches. We programmed the permissive signal here under the POTT scheme, RMB1A. Now let's go to the trip logic down here. And in here, we can program the unconditional trip logic. This is the TR equation. Basically, these are trip conditions that do not require any communications with the remote end. Typically, you would program this, for example, with your zone 1 elements, zone 2 elements, time delayed, any time over current elements that you might be implementing. For this example, we're going to say that we're going to trip on our zone 1, our zone 2, time delayed, or an over current element 51T01. Just as an example, again, this is the unconditional trip. What I want to focus on here is this communications assisted trip equation. This is basically the equation for our POTT scheme. For this example, I'm going to program this simply to Z2P. Here, essentially, you would program any elements included in the POTT scheme. In this case, Z2P is the phase Mo element that we programmed. And note here that typically you would also include an element that can also operate for ground faults, which I've excluded again from this example just for simplicity. Now this equation will declare a trip if the condition we programmed into the PT1 equation, again, the one over here, if those two conditions are met. Again, let me repeat that because that's very important. This equation is going to declare a trip if the condition that we programmed in the PT1 equation is also met. In other words, as we discussed, if the local zone 2 element picks up and the remote end zone 2 element also picks up, which we know of via the RMB1A bit. Now here, of course, we also need to program the condition for which we're going to send a permissive signal to the remote end. And we're going to do that again using the SEL proprietary mirror bits channel. So here I'm going to go to port 1, which is the one that we're going to be using for our mirror bits communication. I'm going to program this to be mirror bits A. So I'm programming a port in the relay to implement a mirror bits communication. Then I can go to the TMB1A equation, which is the transmit bit number 1 over the mirror bits channel. So here, let me do a search TMB1A, and that is down here. So basically, this is again mirror bit 1 channel A equation. This is going to be our transmit bit number 1 over the mirror bits channel, which we want to be our permissive to the remote end. This is going to be relay word bit key, which we're going to talk about here more in a second. But this is basically the transmit signal that permits the remote end to trip on its zone 2 element for the POTT scheme. All right, so we programmed our relay. Let's talk a little bit more about some of the internal logic for the POTT scheme, which we can find in the instruction manual. All right, so what I want to show you here is the key equation, which is on page 444 of this PDF, which is the one that we just programmed into the transmit to the remote end. So I'm actually rotate this and let's zoom in a little bit more. So the bit that we programmed into our transmit bit is this relay word bit over here, key. Now, if you follow that back over here, so going over here over my mouse, you can see that that comes from the TR-COM equation, which we programmed to be our zone 2. So in other words, what this is doing is, since we programmed zone 2 into this equation, TR-COM, that's going to pick up this bit key when it picks up, and it's going to transmit our permissive signal to the remote end. Now there's more equations over here. This deals with the current reversal conditions. Again, I'm excluding this for this example just because that gets a little bit more advanced. But basically, if there's no current reversal conditions, which is somewhat rare, especially when there's no close by parallel paths between this transmission line and another transmission line, when we don't have those conditions, basically the key bit becomes essentially whatever we program into the TR-COM bit, which is usually our zone 2 phase, ground, maybe some overcurrents, any elements that we want to include in the POTT scheme that declare a forward fault. All right, so I just want to go over that because that's a word bit that it's kind of hidden inside internal logic of the relay. And again, that's what we're going to program for our transmit bit. So in our settings, we programmed the CT ratio, the PT ratio, the line impedances, the reaches of our Mo elements, including the zone 2, which is the one that we use for the POTT scheme, as well as the communications assisted tripping equation, which is a TR-COM equation, as well as our permissive signals both being received from the remote end and being sent to the remote end so that our POTT scheme functions properly. Alright, so that's how you program a POTT scheme using the SEL-411L relay. Now remember to download our Protection and Control Fundamentals PDF. The link is in the description below. And if you like this video, make sure to hit the like button and subscribe to the channel for more videos about power system protection and power engineering, and we'll see you in the next one.